that the club is now in possession of an 8-inch Skywatcher Daub with a whole bunch of eyepieces and Barlow lenses, as well as I think a moon filter and a collimating lens for the Daub. So that'll be a part of the library. So that's going to be available to anyone who wants to loan it out. I have it here at my house for the time being, and we'll go from there. And it was quite the quite the generous gift to the center from someone out in emo. So, okay. So this is going to be the sort of the public talk to for introduction to exoworlds and what they are and why they are important to astronomy in the modern context. So we'll have to start with the background for us. So we live in the Milky Way galaxy, a galaxy with 200 to 400 billion stars, with current estimates. 100,000 light years across, 15,000 at the center bulge, about 3,000 light years in thickness through the disk part of the galaxy where the spiral arms are. 12,000 light years thick at the central bulge. So within the galaxy, these 200 to 400 billion stars, with our current estimates, may very well all have, or a large number of them will have planets orbiting them. We're still trying to observe the night sky and determine how many planets, from a statistical perspective, are likely to be out there. But they're super hard to find. So what you see in front of us is when we look at the night sky, we use a magnitude system. And you can see it's sort in reverse. So the negative numbers are the brightest and the bigger numbers are the faintest. So the sun being somewhere between -25 and -30 magnitude. The full moon tonight being around -13th magnitude. The brightest star, Sirius, just over -1. The brighter stars that you can see with your eye are around one to third magnitude. And the brightest stars, or the faintest stars that you can see with your naked eye, are around 6th magnitude under a dark sky. Now, the fainter you go, the more professional telescope and larger telescopes that you need. So when you get down to around the 25th magnitude, that's about the limitations of ground-based telescopes, even with our technology now, because the atmosphere just absorbs too much light to see anything beyond that level. The Hubble Space Telescope can get down to around 28th magnitude. And I don't have a current estimate to the magnitude range of the James Webb Space Telescope. Now, it's important to keep these numbers in mind because exoplanets are going to be much fainter than the 30th magnitude. And in the situations where we can see them, we're going to have to devise a method to blot out their host stars, because the host stars will be so much brighter compared to the host planet that we won't be able to see the planet because it'll be lost in its host star's glare. Now, if we were to build a telescope even larger, at some point, we could actually start seeing the planets and then features on those planets. And that's going to come coming in years to come here. So the first question we have to ask as astronomers when we're looking for exoplanets in the night sky, starting out with a blank slate, is, do different types of stars offer different types of planetary systems, or do they create different planets? Do they have big planets, small planets, multi-planet systems? Because we just don't know, and we haven't seen enough yet to know that. So we have to look at something like the Russ-Herschel diagram. So this is a diagram representing all the stars categorized within the galaxy and presumably within the universe. So if you look at the Russ-Herschel diagrams, the stars in the middle here, making up this middle arc, are stars which you normally think of as stars that are living. They're converting hydrogen into helium in their cores. They're still what we call being on the main sequence. And their lifespans vary by age or vary by mass. So the top left corner are stars that are super massive, super bright, and have a super short lifespan. There's a relationship between how much mass you have and how fast you go through your hydrogen to helium fuel. So the stars in the top left corner can rip through their hydrogen fuel supply in as little as 100 million years. As you move down and to the right, to the bottom right corner, the lifespan of stars continuously increases. As you get down, you get from bluer stars to less blue stars into yellow, like the sun, where lifespan has gone from 100 million years to almost 10 billion years. And as you go further down to the right-hand corner, you go from yellow to orangey stars to red stars. And when you're at the very bottom, these M-type stars, you have a lifespan of a star that is nearly 1 trillion years old. They only have a fraction of the mass of the sun, and some of them are not much larger in terms of diameter than, say, the planet Jupiter. Now, the question is since stars are so variable, do the planets that go around them relate to how big the star started out in mass, or is there other factors to consider and not just simply the size of the stars? So the first thing that we should decide to do, just because it's easiest to get our feet wet in this process, is look for brown dwarfs. And the reason that we look for brown dwarfs is because they should be easier to detect because they're much larger than a planet, say, the size of Earth. They're the in-betweens between what we consider a star, and use air quotes there, and a planet. I didn't realize I had a timer on this. So we kind of have a good idea of where we should look for brown dwarfs, although they have come up, the ones that we have now discovered have come up in some surprising places. But we have some good ideas of where we should be able to find them readily, easily. And that place is in young star clusters, like the Pleiades, somewhere in the Orion Nebula, if they become closer to us. So brown dwarfs are technically stars. We have decided that we're going to classify them as stars, although they're not big enough to sustain hydrogen to helium fusion in their cores, which is one of the definitions of what a star does. They do convert another element into higher elements to give off heat. And the second process that they go through is still contraction. So brown dwarfs are giving off more heat than they would receive from their exterior sources. And this means that they glow very brightly in the infrared, which means we can use ground-based telescopes as well as radioactive telescopes or space-based telescopes in the infrared to try and detect them rather than do a direct observation. So where do we look? Well, we want to look in places with star clusters, places with double clusters, or just try to grab a large area of the sky. So one of the things is that we can use different types of methods, and I'm going to talk about those methods later when we're talking about discovering planets, because it's the same process. But the important thing to understand about brown dwarfs is that it's a jumping off point for us to hone our skills to find smaller planets that we're more interested in, and planets that are more likely to support what we're really interested in is life as we know it. And we have been successful. We have discovered quite a few brown dwarfs throughout the galaxy, most of them fairly close to us. So the first brown dwarf was around a star called Gliese 229. The brown dwarf got the designation 229b. It has 35 times the mass of Jupiter. It's 6.3 park seconds away, which is basically 3 light years for every one. So almost 20 light years. We'll round that number from the solar system. And then after observing it, they use the spectrum from the star and the star's light to determine a signature that shouldn't be there, which is methane. Star would be too bright to keep methane in its atmosphere. So the only reason that you would have a signature in a star's spectrum with methane is because there is a brown dwarf in orbit around it. And we were successful eventually at directly imaging it with new technology. So you can see in the image that we can actually spot the brown dwarf in orbit around the star. And as our technologies have progressed, using brown dwarfs, we can use an analog towards a solar system and also as Jupiter. So if a brown dwarf is somewhere between a planet and a star, you can think of it as having either a solar system or it should have moons. So that led to the idea of looking for something in orbit around brown dwarfs, and we have been successful at finding a planet in orbit around a brown dwarf. But if we want to understand dwarf planets and exoplanets, why they're important to us, where they are in the galaxy, what they're made of, and where they come from, and potentially how they evolve, we have to understand how they should form. So our best theory is that planets form around their host star as their host star is forming. And they form from something called a protoplanetary disk. And basically, all this is dust and gas that hasn't quite yet spiraled down onto the main star. And it's starting to condense out around the main star. And if you think of the rings of Saturn, it's sort of the same process, that this material has begun to spin, it's flattened out into the pancake, and it's got enough energy and enough angular momentum now to keep spinning and not collapse onto the center star. The further out you get from the star, as our theory believes, is that you have different phases within this planetary disk. The closer you get to the young star, the warmer it should be, so you should not have as much lighter materials like gases and water. That should be out in things. So we have a place called rock line, and if you're within the rock line, you should see terrestrial planets because there's not enough material sitting there because it's been blown away. When you get further out and you get to a certain distance from that star, you get something called a snow line, where water and other types of gases are able to condense out of the cloud and form crystalline, which then condenses into a small planet and then gets eaten up by planetesimals and other objects that hopefully will eventually form large planets. Now, protoplanetary disks, propylids, were discovered by the Hubble Hubble Space Telescope back in the late 80s, just after the telescope received its corrective lenses. And you could, when astronomers looked into the Orion Nebula, you could see around the brighter stars that they had these strange little shapes around them, in which astronomers determined were little pockets of gas bubbles being blown away from the star. And that was exactly what they were looking for, because that should be an indication of a planetary disk being formed around these stars. Now, if we see a star cluster like the Orion Nebula, which is young and still forming stars doing this process, then it stands the reason that every star cluster went through this process when it was formed, which means these protoplanetary disks, and this image tells us that planetary disks are probably pretty common throughout the universe, which gives a lot of credence to the idea that planets may be common. So we fast forward into the 2000s with new technologies and new radio telescopes, like the ALMA array in South America. We're absolutely able to build on the work of the Hubble Space Telescope, and using a different wavelength, we could see into these protoplanetary disks, and we could see that there was something going on. And our new technologies, as we continue to advance, we get to see new things, and we get to learn new situations. Now, if you look at all of these, they all have something kind of in common, and that's they kind of look like the rings of Saturn. If you can picture Saturn being in the center, they all kind of have the same kind of features that we can see with Saturn, which is one of the important things about exoplanet and exoplanet research. We're starting to see things out there that relate to things that we see back here. And if we can connect the dots properly, we can understand our history of the solar system by looking at what's out there and apply that information back here on Earth, or back here in the solar system. So that's one of the most important things about exoplanet research at this point in time, is that we are learning more about the solar system, because we can look at other solar systems and other things that we're seeing out there and apply it back to our solar system. Unfortunately for astronomers, we only get to see our solar system as it was. We can't look at it as it was in the past because we weren't here. But looking at other solar systems give us the opportunity to sort of glimpse of what our solar system might have looked like back in the past. And one of those things that we have already learned is, and can apply to here in the solar system, is the planet Neptune. So we knew that something was sort of weird with Neptune, that it may or may not have formed where it was, close in the solar system. And another thing that we saw in the solar system that we couldn't explain is something called the Late Great Bombardment. And that was a period throughout the solar system where there was a second wave of comet impacts in great numbers against all the celestial bodies. So all the moons, all the planets, including Earth, were hit by a lot of debris for a few million years. By studying exoplanets and learning about exoplanets out there, we have learned that planets can move quite a bit in the early development of these solar systems, and that Neptune is one of those examples. I wanted to go back here. So Neptune, we can kind of call the black sheep of the family, and at some point was kicked out of the solar system, or likely kicked out of the solar system, probably by Jupiter, an interaction with Jupiter and Saturn. And the only reason that we still have it here is in our solar system is because it was plowing as it was getting kicked out, it started plowing through the back end of the solar system, through the Kuiper belt. And the process of plowing through the Kuiper belt, kicking up all those comets and directing them, all those bits of debris, kicking them into the inner solar system, slowed it down enough to stay within our solar system and caused the great late bombardment that we see now. So those two things are related, and we would not have realized that if it wasn't for looking at how other solar systems form. So there's a few ways to detect exoplanets, but there's three particular main ones. So you have the radial velocity method, or the wobble method. So if you look at a star's light, its light shifts from red to blue as that star is being tugged on by an unseen body. Another method is the light curve, which when we're watching this star, it'll go through periods of brightening and dimming. And that can tell us that there's an unseen companion there as well. And the third is, well, if we have a telescope big enough and camera sensitive enough, we could just directly photograph that object. So again, the process of which we use to look for exoplanets was developed for doing other things, in this case, binary stars. So we didn't develop a new process to look for these exoplanets. We looked to our knowledge base that we already had. And binary stars and our research in binary stars and our understanding of physics to go with it can be simply scaled to looking for an object orbiting a star. So the same processes that you see here. The top one here is basically the wobble method. So you have a center of mass. As an object orbit a mass, both objects orbit a center of mass. No matter how big or small the object is, it will force every object in that body, in that system, to orbit around a center mass. So just because a planet is so much smaller than a star, say the Earth to the sun, the Earth still forces the sun around a common center of mass. It just doesn't do so. It doesn't make the sun move very far. Now, you can see at the bottom here, these colorful bands of light. Well, that's spectrum. And if we look at the spectrum of these stars, we can see that these absorption lines, so elements that are in the star's atmosphere, will move and they'll shift towards the blue or towards the red. And that's a position that there should not be in. So that's how we know that something is making a star move towards us or away from us. The second method, the light curve, is just simply, we can't see the planet. It's just simply too small. But as it passes in front of the star, it blocks out just a little bit of that star's light. Now, we've all seen a transit of Mercury. Some of us have seen the transit of Venus. Well, that's a really close example, and it's the same example, except on a much closer, grander scale. Now, out there, we're not going to be able to see the planet because it's just simply too small. We'd never be able to resolve it against the surface of the star. But nonetheless, it still results in this light curve that you see here, where the star's brightness is continuous. It dips for a bit, lasts for a little bit of time, and then brightens again. And that's a telltale sign that something is passing in front of the star. And if you can count, if you go back to the star night after night, you can see this curve. You can pick out that there's an orbit of something going around. And from there, you can start working out details of what this object might be. Now, it's just the same thing as eclipsing binaries that we've already been familiar with and that astronomers like in the AVSO have done for years. So they've already worked out how to do this process, and then we just have to apply it to extrasolar planets. And we have done this. And what you see here is actually 4 planets in orbit around a star. Now, as I said before, we could directly measure them, but one of the problems is that the host star is really bright. So you can see this star here that's been certain. So they use something called masking to dim the light from the host star so it wouldn't blind out all these 4 little planets that are going around. So here's the first discovery, which was kind of a shock to astronomers. It was announced that 3 planets were orbiting a pulsar, which was big news in '92 because it was the first planets discovered outside the solar system, the first planets discovered in a multiplanetary system, and the object that they were orbiting was a surprise. No one thought that planets could survive around a pulsar, or that they could form after a supernova had happened. So there was a lot of things that happened there in that one. But the big news, the one that gained the real headlines and lit up all the stations, was 51 Vegas IB in 1995, a Jupiter-like planet orbiting a sun-like star. And now the race was on to discover planets around other stars. Today, we have over 5,000 confirmed planets. 1,600 of them are gas giants like Jupiter. 1,700, well, we'll call it 1,800, are planets categorized as something like Neptune and Uranus. So a certain type of mass and a certain type of diameter. We have something that we've learned about astronomy, about other solar systems, and this is probably the most interesting thing, is that this is super Earths. About 1,600 super Earths have been discovered, and that's a planet about twice the mass of our world. And it is a feature that we don't have in our solar system. It's starting to look like super Earths are common throughout the galaxy. And for some reason, our solar system could be an odd character out and not have one of these super Earths. So far, we haven't had much luck, but we've up to almost 200 terrestrial planets. So that's planets like the Earth, Mars, and Venus, and 5 that still are waiting classification that don't fall into any categories nicely. So exoplanets are important because we can learn a lot from them. And they can answer some pretty fundamental questions. So we can learn about atmosphere processes, different atmospheres in different worlds. What are carbon cycles, water cycles? What kind of other cycles might there be with their different compounds doing different things in the way that water functions here on Earth? We can look at their chemical properties. Are we seeing different chemicals that we don't see on Earth? Are we seeing a lot of the same chemicals that we see here on Earth? How do they interact with one another? We can learn solar system formation, what type of solar systems are common, what type of solar systems are not common. And of course, the big one that we're really interested in is, of course, life. Are we going to discover that we are not alone in the universe? And as technology has gained and then our understanding of exoplanets has grown, everyone here can actually follow the light curves of exoplanets. There's a number of space-based missions, including the RASC, where you can simply use a telescope and a DSLR, or just a straight plain DSLR to pick up, goodness, to pick up the light curves of extrasolar planets. The robotic telescope program the RASC runs actually has data for some of those targets. So if you want to download that data, you have access to it, and you can see the light curves for some extrasolar planets. Now, NASA has an extrasolar planet website, and as you can see, there is a lot of confirmed candidates, a lot of potential candidates. So almost 9,000 candidate planets that need to be confirmed, as well as, and those planets occupy 3,800 multi-planet solar systems so far. So that's a little bit on exoplanets. Any questions from you guys? I see both Doug and Doug and Tracy have run away.
No, I'm here. I'm just trying to unmute people.
I'm still here.
Okay. All right. Does anyone need a break at this point?
I'm going to stop the recording, and if anybody has any questions, and they don't have to be shy about it.